So throughout section 2.3, there is a set of limit laws, and you should know them and know how to use them. You're going to need to study them and even memorize them, and they will be beneficial. In this video, what we'll be using is the limit laws in a variety of ways to find different limits. All right, so we'll be talking about them, but we're not going to go over, and I'm not going to just like rehash them, because the fact of the matter is they're written inside of the textbook. You need to go in, take a look at them in the textbook. It's kind of a waste of our time. Let's go through, let's learn some ways to go about doing calculus, right? Okay, and you can go through it and look through all those limit laws, and we'll even go through some of them inside of class, just so that you get the notation, okay? So the first thing that we want to talk about when we talk about finding limits is this idea of direct substitution. So if f is a polynomial or a rational equation, that's rational, r, not a national equation, and a is in the domain of f, so that's very important. A has to be in the domain of f. Then what we can do is we can just directly substitute, basically saying the limit as x approaches a of f of x equals f of a. So what you'll do is you'll go in, you'll say, okay, well, is f a polynomial? Is f a rational equation? And then is a in the domain of f? All right. So like, let's say, for example, I have this, the limit as x approaches 2 of 1 over x squared. 2 is in the domain of f, right? 1 over 2 squared is going to equal 1/4. So that's 1, that's true. And 2, f of x is a rational equation. So that's the second need. So this whole thing is going to then equal 1 over 2 squared. We just directly substitute, and that'll be 1/4. So that's it. Limits where what we have, like I said, are a polynomial or a rational equation. As long as you're not, finding it at a value that's undefined, then what you can do is directly substitute. Now, sometimes what will happen is we'll have a problem. Okay, we'll have a problem where, like in this case, we have a rational equation, x plus 1 over x squared minus 1. Okay, so that in fact is true. That's a rational equation, but -1 is not in the domain of f. Basically, the problem here is that -1 ends up giving us 0 on the bottom. Okay, however, if what we can do is we could actually do some algebra, right, to give us this limit, then we can use direct substitution again. Okay, so in this case, what I'm going to do is I'm going to take, okay, I got the limit as x approaches -1 of x plus 1 over, and then this is going to be x minus 1 times x plus 1. So this is then going to equal, we can cancel these two out, it's going to be 1 over, it's going to, excuse me, it's going to be the limit as x approaches -1 of 1 over x minus 1. And what you'll notice, this is one of the ones that we did in inside of the intuitive ones, is that this is now, we can now, excuse me, now -1 is in the domain of 1 over x minus 1. That's not f, but it's similar to f, okay? So we can now direct substitute. Okay, so this limit is then going to equal 1 over -1 minus 1, which equals -1/2, which is what we came up with before. Okay, notice f of -1 is undefined. So that's still true. If you plug in -1 into this into f, x plus 1 over x squared minus 1, you're still going to get an undefined statement, 1 over 0, or excuse me, 0 over 0, right? That's not going to work. But the limit as x approaches -1 of f of x equals -1/2. It in fact is defined. All right. So we can use algebra to basically remove the problem area, like remove that x plus 1 term, and that'll allow us to find the limit. Now, what we have going on here is something actually quite similar too. We're going to use some algebra in order to find the limit here as well. Okay. Excuse me. This is the limit as x approaches 0 of the square root of t squared plus 9 minus 3. Now this is going to end up giving me, right, the square root of 9 minus 3 over 0 squared, which equals 0 over 0 if I just plug in f of 0. Okay, so that's undefined again. However, if I do some algebra, I can actually make this defined. So what we're going to do is we are going to multiply by the conjugate, excuse me, of the square root of t squared plus 9 minus 3, or the square root of t squared plus 9 plus 3. So this is what we're going to multiply by, top and bottom. So this is a very standard trick that we do, not only in algebra, but it's going to kind of come up a lot inside of calculus, is by multiplying by the conjugate, we end up finding a difference of squares. So we're going to get the limit as x approaches 0 of the square root of t squared plus 9 minus 3 over the square root of t squared plus 9 plus 3, over t squared, times the square root of t squared plus 9 plus 3 over the square root of t squared plus 9 plus 3. So as you get more mathematically sophisticated, what you're going to notice is this thing here equals 1. And that's why we can multiply by it, because it doesn't change anything. You multiply something that's the same on top and bottom, it's equal to 1. It's like multiplying by 1. In fact, it's the same. What it does allow us to do is it allows us, okay, to transform our function in a way that allows us to do some algebra. So we're still going to get the limit as x approaches 0, but this thing here, notice this is a difference of squares. So this is going to then be, right, t squared plus 9 minus 9 all over t squared times the square root of t squared plus 9 plus 3. So this is now going to be the limit as x approaches 0. Our 9s are going to cancel, so I now have t squared over t squared times the square root of t squared plus 9 plus 3. And that's thus going to equal the limit as x approaches 0 of 1 over the square root of t squared plus 9 plus 3. Now, in this case, again, 0 is actually in the domain of this particular function, so I can directly substitute. So this is going to be 1 over the square root of 9 plus 3, which equals 1 over 6. So by multiplying by the conjugate, we can do some algebra in which to transform this function into something that we can't find the limit for, or that ends up being undefined, to defining what our limit actually will be. Okay? And it actually allows us to remove that t squared term. We remove the t squared term, and that then allows us to transform our function into something that we can find the limit of. All right? So what the point of me doing this particular section was to emphasize the fact that we oftentimes are going to be utilizing algebra in order to simplify our limits and actually use then direct substitution to find a limit. Okay, so this is one of those things where you're going to have to get a little bit creative. You have to spend some time thinking about it, like kind of working through some of the problems, right? Get kind of creative in the approaches that you take. All right, this is why algebra is so important to doing calculus, because sometimes you just got to transform stuff into something that you can do calculus on. Okay, so this completes this particular lesson.